And we could also have the limit as x is approaching negative infinity. Okay, so we're just asking what number it approaches as x gets really big or x gets really small. So for instance, we might have a number, I don't know, what's so funny? We might have the limit as x approaches infinity of maybe a function such as 1 over x, and you guys know the graph of this, right? This graph looks like two hyperbolas, or a hyperbola. And so as x approaches infinity, meaning that as x gets really big, the function is approaching 0, right? And so we would say that the limit as x approaches infinity of 1 over x is equal to 0. And similarly, the limit as x approaches negative infinity of 1 over x is also equal to 0. Because as x is getting really small, the function is also approaching 0. Meaning the y value is approaching 0, right? Any questions?
Is that just 1 over x?
Yeah. And so we call these things horizontal asymptotes, right? We learned this in algebra. This is a horizontal asymptote. And so a function can have two different horizontal asymptotes, right? Because it can approach two different numbers as x gets big or as x gets small. Typically they're the same, but sometimes they're different. Horizontal asymptote. Huh? Okay, good. Any questions about this?
What would a vertical asymptote look like?
We already learned about those, right? That's a vertical asymptote. Okay, let me talk about 3 rules for finding these for rational functions. So let's look at 3 different cases. Okay, case 1. Suppose we're looking at the limit as x approaches infinity of a function maybe like x plus 2 over x squared plus x plus 1. Okay, and we're asking the question of what value this number here, or this function here, approaches as x gets really big. So, we could try plugging in some numbers. We could maybe plug in 100, right? If we did 100, if x equals 100, we would get 100 plus 2 over, what is 100 squared? 10,000? 10,000 plus 100 plus 1. And if you calculated this, that would be about 0.01, right? If you did maybe x equals 1,000 or 10,000 maybe, so 10 to the 4th, then the numerator would become 10,000 plus 2, but the denominator would become, what is 1 with 8 zeros? 100 million, right? 1 0 0 0 0 0 0 0 plus 10,000 plus 1. And that would equal about 0.0001, correct? And so as we can see, as x is getting bigger and bigger, the function is clearly approaching 0. And so we would say that the limit as x approaches infinity is equal to 0 in this case. And we notice that this is the case because the denominator is clearly getting a lot bigger, a lot faster than the numerator is, right? Because in the numerator, the biggest number is always going to be the x. But in the denominator, the biggest number is x squared. And x squared increases so much faster than x, such that the denominator is always much bigger than the numerator for large values of x. And so, as you can see, when we plugged in 10,000, the denominator was becoming 100 million, while the numerator was still stuck at 10,000. Okay, and so this gives us our first rule, which you guys should know, which is that when we have a fraction, when the degree of the numerator is less than the degree of the denominator, then the limit is 0. So the limit as x approaches infinity is going to be 0. Okay? Very good. And that's because, the numerator and the denominator increase at different rates. Questions about that? I think you guys learned this in Algebra 2, right?
So that's just, you just gave us a number of x.
Huh?
You just gave us a variable of x.
I gave you the
Like,
variable
give
of
us
x?
a variable, whatever it is, we don't have to find the 100.
Yeah, so yeah, when you have this function, you don't need to plug in anything. You just need to look at the degree of the numerator, which is 1 in this case, right? Because the biggest term is x, and that has a power of 1. And the denominator has a degree of 2, because that's the biggest term there.
I'm saying the x is equal to 100, you just gave us that.
It's a test case. We were trying to plug it in to see how the function behaves. Yeah. Okay, let's do the second case. So suppose now we have x cubed. So let's say we're looking for the limit as x approaches infinity of x cubed plus 5x over, say, x squared plus 3. Okay? This limit is going to be, does not exist, or you could say infinity. And the reason why it doesn't exist is because the numerator is going to increase so much faster than the denominator, because the degree in the numerator is larger, right? X cubed increases much faster than x squared. What is this? X cubed increases a lot faster. And so that means that this function is going to tend towards infinity as x gets really big. And so that gives us our second rule. When the degree of the numerator is greater than the degree of the denominator, the limit as x approaches infinity is going to not exist. Okay? Let's do the third case. The third case is when the degrees are the same, right? And so we wonder what would we do in that case. So suppose we had the limit as x approaches infinity of, let's say, 5x to the 3, so 5x cubed plus 7x squared plus 2 over 4x cubed plus 8x, just coming up with random numbers at this point, okay, plus 1. The answer in this case would be 5 over 4, okay? And how do we know that? Right, yeah, good. If you plug in let's say we plugged in a super big number of x, like 10,000. If we plugged in x equals 10,000, then the numerator would be, I don't even want to say it, 5 trillion, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Plus 7, 1, 2, 3, 4, 5, 6, 7, 8, plus 2. And then the denominator would be 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus, I would not be writing this down if I were you, 80,000 plus 1, right? And if you calculated this would be approximately 5/4, right? And why is that? That's because the most quote-unquote influential term in each of the denominator and the numerator is always going to be the 5x cubed or the 4x cubed, right? And like these two numbers are pretty much irrelevant in comparison to those. And so really the only numbers we need to care about are the 5 and the 4 that are the leading coefficients of the highest degree term in each side.
When do you decide that?
It's like 12:44. I don't know why you need to use the bathroom.
When are we done?
12:45?
We have 1 minute.
Okay, so that's the third rule, and I'll just stop there.
Good job, Mr.
When the degree of the numerator equals the degree of the denominator, then the limit as x goes to infinity is equal to the ratio of the leading coefficients.
Because what?